What up, math please? Whoop, whoop. All right, let's do this. This is a rate of change in slope. I believe that's 4.2. It's going to be an awesome lesson. Let's do this. Go ahead and do the warm-up right here. Just evaluate these division problems, see what you get. Okay, pause it if you need to, but let's talk about it. All right, 12 minus 6 is what? 6 over 8 minus 2, which is 6, which equals 1. 9 minus 4 is 5. 4 minus 6 is negative 2. So that's negative 5 halves. That's how I'd leave it. Always leave slope as an improper fraction, please. 7 minus 3 is 4. Those become a positive. Negative 2 plus 2 is 0. So divided by 0, ooh, can't do that. That's nothing. 8 minus negative 4, again, that's a plus. 8 plus 4 is 12. Negative 3 minus 1 is negative 4. 12 divided by negative 4, positive divided by a negative is negative. 12 divided by 4 is 3, negative 3. In 1850, the population of Houston, Texas was 2,400. In 2010, Houston's population was a lot. What is the average annual increase in population for Houston between 1850 and 2010? I don't know. Let's bust out the calculator for that. Goodness gracious. Let's do 2,099,451 minus 2400. 2400 equals okay, and then we need to have, so that's this down. What is that? That's a big number. Sorry, that's 7051. 7051. We're going to divide that by, let's see, 2010 minus 1850. 160. 2097051 divided by 160. On average, the growth was 13,107 people per year. It's actually 106.5, but you can't grow by half. So it's 107. That's what I'm going to say. All right, I'm getting ready to erase this. Ready, set, go. Let's see if we were right. Where's my showing answer button? Yeah, see, look at that. That's undefined, all that good stuff. Boom. He's right. Let's go. Okay, rate of change of a linear function. Got a little learn. Okay, so we're going to talk about rate of change. Rate of change is just how one quantity is changing with another. And so in this case, when we're talking about graphing, we're talking about our change in y over change in x. So our rate of change of a graph is how much is our y values changing in between 2 points divided by our change in our x. Okay? Don't forget, our change in x is the change between two values of the independent variable, and our change in y is the change between two values of the dependent variable. Okay? So write this down. Rate of change equals change in y over change in x. Also, instead of change in, you're going to see me use the Greek letter delta. Boom. I know. You're like, that's a triangle. Yep. Whenever you see me write change in y, that's what that means. Change in. That delta means change in over change in x. It's shorthand. Okay? We're going to find the rate of change right here. Rolling, rolling, rolling. Okay, so for this one, we want to find the rate of change of the function by using 2 points from the table. So let's look. We're going to use the first point, 212. Notice we call these points because they're written as if they could be XY points. That little comma in the middle, right? So what do we see right here? The point 212, the point 424, and 636. We can pick any of these 2 points. They'll come out the same. But I want to look at these 2 points. What is our change in X? Our change in X is plus 2. Over here, what's our change in Y? It's plus 12. So what am I going to do? I am going to find out what is the actual rate of change, and I'm going to do, remember, it's my change in Y over my change in X. So I'm going to have 12 over 2, right, which equals 6. And I could simplify that, by the way, to 6 over 1, which is 6, but it's just 12 divided by 2 is 6. Perfect. There we go. So our rate of change is, we're going by 6 pancakes for every 1 cup of flour. Because I went ahead and divided this out, this is 12 cups of pancake, or 12 pancakes for 2 cups of flour, but by dividing it, we found out for every 1 cup of flour, we're going to grow by 6 pancakes. Boom, right there, perfect. All right, let's keep going on with the rate of change. Let's find the rate of change here. I like them extra examples. The amount of money Shamar earns, Y, after working X hours is shown in the table. Find the rate of change. Okay, after 8 hours, she earns $62. After 12 hours, she earns $93. So what we're going to do is we're going to take 93 and subtract 62 to find out what that growth is. So we're going to take 93 and minus 62. And then on bottom, I'm going to take my 12 and I'm going to subtract 8. Now that's the same thing I did last time. I just kind of went the other way and said 8 plus what is 12? Well, 4. And 62 plus what is 93? Well, in this case, it's easier to do the subtraction. It's 31. So what's 31 divided by 4? It is $7.70 or 7.75, which stands for $7.75 or $7.75 per hour, or $7.75 per hour. Okay. And that's how much she is earning. We can check it. Check, check. Yay, we did it right. I always have to reset it, though, because if I don't, when I teach it live, I forget. Okay, these aren't meant to be long slides, just to kind of go through them, show you what we're doing. So now we want to compare rates of change. So let's look right here. Find the rate of change of the function between 10 a.m. and noon. So let's find time since midnight. So we're going to find 0. That's 4 a.m., 8 a.m. It's grown by 2 each time. So 10 a.m. is going to be right here. So if I'm writing this down, at 10 a.m. And time is x. Remember, this is change in y over change in x. It's great to remember that because then I know my x-axis is going to go on the denominator. So from 10 a.m. to noon is going to be noon is 12 minus 10 a.m., right, to get that rate of change. And then I'm going from 65 to 68. So I'm going to have 68 minus 65. Now you don't actually have to set up this subtraction problem. For a problem like this, I would just say, hey, on bottom, we know that's clearly a change of 2 hours, right? And on top, that's clearly a change of 3 degrees. So that's 3 divided by 2 degrees per hour, or if you divide that out, that's 1.5 degrees per hour. See how that works? Okay. Now it says find the rate of change between 2 p.m. and 4 p.m. Okay, let's do that. So this is 10 a.m. to noon. 10 a.m. to 12 p.m. Let's look at 2 p.m. to 4 p.m. Again, the time goes on bottom, so we know that's going to be 2 hours. I'm just going to do this the short way that I would normally do it. And from 2 p.m., that's 12. I know this is 14, but 1400 hours would be, that's right, military time. So that's 2 to 4 is right here, 2 to 16, or 14 to 16. So that's there, and it's 68 to 68, which is a change of 0. And 0 divided by 2 is just 0, so that's a 0 degrees per hour change. Now, whenever your rate of change is changing, we know it's not linear. And we can see from the graph, this is a nonlinear graph, right? So it changes depending on what time segment you're looking at, what the rate of change is going to be different. Okay, all right, let's move on to the next one. Bring my picture back into play. Will I have to move it in? Let's find out. When the rate of change is the same for any 2 points in a function, the function is linear. So if the rate of change is the same for 2 points, then it's linear. Determine whether the function is linear. If it is, state the rate of change. Okay? Let's find out, is it linear? To go from 11 to 8 is minus 3. 8 to 5 is minus 3. 5 to 2 is minus 3. And 2 to negative 1 is minus 3. Okay. Over here, negative 5 to negative 3 sounds weird, but that's plus 2. And negative 3 to negative 1 is still plus 2. Negative 1 to 1 is plus 2. It's easier to see when you look at 1 to 3. That's plus 2 clearly. Okay, so our rate of change, remember, it's that change in y over the change in x, which is going to equal, what's my change in y? Well, it's plus 2. What's my change in x? Negative 3. So you could state that as a decimal. I'm not going to, because this is going to be 0.6666, right? Negative 0.666. Let's just leave this 2/3, or even round it to negative 0.67. All right, so that's negative 2/3 rate of change. Let's go ahead and scroll down here. Write this down, though. All right. So the rates are constant. So the function is linear. The rate of change is negative 2/3. Boom, right there. Check answer. Yay, uncomfortable noise. Determine whether the function is linear. So we got to find out if it has a constant rate of change. So let's find out. Let's look at it. 1 to 2, that's plus 1. 2 to 3 is plus 1. So it's plus 1 all the way down. We see that plus 1, right? All the way down. Over here, let's look. Negative 4 to 2 is plus 2. Negative 2 is plus 2. Negative 2 to 0 is plus 2. 0 to 2 is plus 2. Which means it's absolutely linear because it's a constant rate of change. It's going up 2 in the y for every 1 in the x, which is just 2 over 1, or a rate of change of 2. And is the function linear? Absolutely, the function is linear. Boom. Awesome. Okay, determine whether the function is linear. Well, I see right here it's going up by 7. Looks like it's up by 7. Looks like it's up by 7 again, 7 again. Okay, and this is going up plus 3. Oh, but this looks like plus 2 and then plus 3. So let's flip the card and look at this one. Notice it's going 7, 3, up by 7, up by 2. Oh, yeah, up by 7 again, up by 3, up by 7, up by 2. Now, some of you may be tempted to say, oh, well, that's a constant pattern, 3, 2, 3, 2, but that doesn't matter. Has to be the same number, and this is changing between 3 and 2, so this is non-linear. This is a non-linear function, okay? All right, Tomorrow we're going to talk more slope. With that said, peace out.